Thanks for the kind introduction. We have a lot to cover here, so we're going to jump right in and get to it. Doing J1939, and the allocated time is just about impossible here, so we're just going to cover some of the fundamentals and the basics. I'm going to skip the agenda because you'll see that as we go, we're going to talk about different parts of the communication stack. So here's the communication stack, my way. Got the CAN network out here, a simple network. You've got a physical device attached to it. You have a physical layer in the stack. You have a data link layer, transport and application layers, usually shown with application on top. I like to show it this way. Your physical layer is best understood by realizing its primary function is getting ones and zeros reliably across the network. These are the J1939 specifications that cover physical layers, 250K twisted pair, shielded cable, 500K twisted pair, and CAN FD out here on the end. Once you can get ones and zeros reliably across the network through the physical layer's job is done, and it passes CAN frames, or those ones and zeros, to the data link layer that assigns or puts them in CAN frames, understands CAN frames. And the main part of the CAN frame is the identifier and the data phase. There's a CRC, there's some control bits in here, but the data link layer understands all that. The J1939 specifications that define the data link layer are -21 for classic CAN and -22 for CAN FD. Transport layer we have one quick example of, and that's when you have larger blocks of data, you need to break them up and send them across multiple CAN frames, reassemble them on the other end. That's what transport does. To some extent, the -22 specification, the CAN FD, J1939 over CAN FD, is just a transport specification, a transport method, because we didn't really repackage the whole -21 definitions to go into the take advantage of the CAN FD advantages there. The applications layer, 95% or so of the work in J1939 is done on the applications layer, and this is where you actually understand signals and frames and messages and get something out of what these other layers, these lower layers, do here. The applications layer is where the point is made, where the data has to be understood and applied, and where J1939 is sometimes even called an applications protocol, although it defines certainly the lower layers. We'll hit on the physical layer. These are general physical parameters, reviews from CAN basics fairly quickly. J1939 network is made up like any other CAN network of a trunk cable, a couple of terminators, a number of devices, ECUs or other dropped off that trunk cable. It's two wires. There's only two wires in a twisted pair. If you look at the voltages on those wires, at the transmission of different bits, it's called a differential signal. Nothing is referenced to ground, they're referenced to each other. You've got a recessive bit during a bus float state. You've got a dominant bit for a start bit to start any frame. And then you go on from there with the recessive and dominant to transmit the data. Over here on the right, you see a collision. Node A and node B both go from a recessive to a dominant state, start transmitting a frame with a start bit. So there's a data collision here. Any digital communication scheme has to handle collisions. CAN does it very elegantly and eloquently and with bitwise arbitration. Okay, so in this third time slot here, node A starts transmitting a 1 or a recessive state, node B a 0. Node B wins arbitration by nature of the bus and never loses any bytes, never suffers a bandwidth hit, and never knows anybody else collided with it, and goes on and transmits its CAN frame. That's bitwise arbitration. That's pretty much all I'm going to say about the physical layer, and we'll move right on to where most of this presentation is going to take place, is in data link and applications. So CAN frames and -21, the classic CAN data link definitions. Here I'm just showing some basic CAN data as captured by CANKing, a free bus monitor for raw CAN data and DBC file functionality downloadable from Kvasser.com website. It's a good application for raw data. I show CAN frames here. I show them in a J1939 formatter. So the priority, the identifier, and the source address here, these are J1939 definitions of the identifier. We'll get more into that later. Data length code of 8. Each one of these frames has 8 data bytes associated with it, a timestamp put on by the application, and a direction indicator. Let's take a look at one frame. This is a smaller frame. This is a frame with 3 data bytes. This is a request frame as grabbed by a different tool. So the identifier is not broken down for J1939 standards. We're going to have to do that. So we're going to use this as example 1. We're going to take a look at this sequence in yellow here of hexadecimal characters and break them down and understand the request message as defined in J1939. So any J1939 CAN frame is broken down as above here. So you've got a starter frame, a priority, a parameter group number, a source address, all part of the identifier. You've got a data length code, you've got some number of data bytes, and you've got a cyclic redundancy check. The green stuff is stripped off by the CAN controller. The applications see what's in yellow and blue. In yellow, you have the identifier, 4 bytes, just short of 4 bytes, because these bits are never sent. The first byte is just represented as a byte, but it's only 5 bits. So your priority here, how do you get a priority of 6 out of 1/8 hexadecimal? Well, you do it because these 2 bits are control bits, and we'll mention later. So there's our priority of 6. In our identifier, our PGN is EA00, as shown here. Translates the decimal 59904, the request PGN as identified in J1939-21. And source address F9, in this case, identified in the J1939 digital annex. And F9 is a service tool. A 249 decimal is a service tool. So we already know that in this request message, a service tool is requesting, with a priority 6 message, something. It's requesting this data right here. It's requesting 00C100. That is PGN decimal 49408, also known as a DM21. The service tool is requesting, with a priority 6 message, a DM21. That's what this tells us. You can trace all that back to the specs. It's a good thing to do to understand a message. You can take any message apart with this method, from raw data to actually what it's doing. It's a very, very good exercise for understanding more about J1939. The parameter group number is very important. Let's look more closely at that. So as transmitted in J1939, the 29-bit identifier consists of 3 priority bits, 18 bits for the parameter group number that are broken down in the spec-21 in the extended data page, the data page, 1 bit each, 8 bits for PDU format, and 8 bits for PDU specific. Again, don't have time to go into those real detailed, broken down in -21, J1939-21 specification. The source address comes after that. That's a 29-bit identifier as used in J1939. So moving on from there, let's quickly look at CAN FD now that we have a basic understanding of the fundamentals of classic CAN. CAN FD adds 2 things to classic CAN. It adds the ability to do a bit rate switch and transmit the data bits at a higher rate. Classic CAN uses 1 bit rate for the entire CAN frame. In J1939, that's either 250K or 500K for the J1939 classic CAN frame. In CAN FD, when J1939 uses CAN FD, it transmits the ID at 500K and it switches, it bitrate switches up to 2 megabits for the data phase, and that's allowed in CAN FD. The second difference is classic CAN has a maximum of 8 data bytes in the CAN frame. CAN FD has a maximum of 64. So J1939 FD uses these extra data bytes in these increments of 0 through 8, 12, 16, 20 on up to 64 bytes. So we're making use of that larger payload in the data bytes, and we're also making use of the faster transmission method by having bitrate switching and going up to 2 megabits for the data phase. Okay, here is how it's implemented in a nutshell, and I can't get into too much detail here because of the amount of time I have, but we've taken the classic CAN J1939 CAN frame, stripped some stuff out that's going to be common between a number of frames. We've identified the contained PG, added a few fields like the type of service, trailer format. We've added additional protection, safety, security, and functional safety protection out here, and used this larger payload of up to 60 bytes in a little bit of a different way, packed additional classic CAN frames in them. So that's how we're using. We're basically using J1939 FD just as a transport protocol. And here's a little more detail about it. An example where we're putting 3 contained PGs, as defined in the previous slide, into one J1939 FD package or CAN FD frame. So we've got some identifier information that we stripped out, again, of each one of these contained PGs, all coming from the same place. We've put 3 different contained PGs in here, 2 standard 8-byte PGs, and this last one we've defined with some assurance data on the end of it. And there's a CRC on the end of the actual CAN FD frame. Here's some definitions of these fields: type of service, trailer format, the payload, contained PG, and some facts about it here. It's basically, again, using transport protocol, using J1939 FD, the capabilities of a CAN FD frame as a transport protocol for classic CAN frames for this definition. J1939-22 is a very complicated and well-written document. You really need to study it to fully understand this concept. These are just the very basics. Let's jump into the data now. I think it's time to take a look at the data and the DBC file and see how the data is transmitted during the data phase of a CAN frame, the J1939 frame. So CAN frame can include 0 to 8 data bytes, a classic CAN frame. Most of these by far can include 8 data bytes. We saw a control frame and took that apart. That included 3 data bytes. Here's some further examples of 8 data byte frames, classic CAN frames. J1939, the ID phase is taken apart in per J1939 standard with the priority, the PGN, the source address. We understand those now. This particular PGN is an F004. We're going to use this data as our second example and understanding how the data is represented. Here's a timestamp put on by the application, and it says this data was received with that R. DBC files label, isolate, scale, and offset the data in any J1939 frame. They're also used in some other protocols as well. So here we have a device reading the raw CAN data, shipping that data through a USB or other bus interface, depending on the application, to a computer or an embedded processor. That processor combines that raw CAN data with the information in the DBC file, and it comes out with meaningful data. It isolates, scales, and offsets that data, again, identifies it via the identifier, and makes meaningful data out of that hexadecimal data coming across in the frame. Let's take a look at an example of how we're going to do that. We first have to understand the parameter group number and the suspect parameter number and how they're defined within J1939-71. Understanding the SPN is fundamental. A suspect parameter number is an SPN, and it's an identifying number for a single parameter or a signal, right? An SP, or a suspect parameter, is the data, is that particular data within that parameter group. There's over 20,000 SPNs documented and defined, completely defined in J1939. They're all listed in the digital annex, the J1939DA, which is a spreadsheet. You turn on filters, you filter on SPNs and PGNs, and you can get anything you want out of there. Right? An SPN can be 1 bit long or any larger number of bytes long, bits long, all defined in the DA. An SP is broken out as far as it can go. You're not going to break it down any further. That's it. Here's an example, a quick example of a message that would contain 4 different SPs. Each of them are 2 bytes. 4 different SPNs. Each of them are 2 bytes. Resolution, offset. A quick example pulled out of the digital annex. So we're going to get into example 2. Here's that data we saw earlier, again broken down in a J1939 format in the identifier phase up here. We're going to worry about the data across the bottom here. You see across here, you see 8 data bytes, timestamp, and it was received. Okay, so the PGN was F004. That's a decimal equivalent of 61444. The digital annex tells us that's the electronic engine control 1, EEC1. If anybody wants to do this on their own, you have to have the digital annex, filter on it, and find this signal. It will give you all this information. Okay, so find this PGN or this message. So we're going to look at engine speed, which is one signal within that message. The signal is identified as SPN 190. The digital annex tells us that this is engine speed, and it conforms to slot 76, which defines how we represent that data. Okay, again, pulled right out of the digital annex. The PGN in decimal, its acronym. This message is 8 bytes long. The signal we're interested in, SPN 190, resides in bytes 4 and 5. I've turned those blue here. Okay, 2 bytes long. There's a resolution of 0.125 RPMs per bit. This is engine speed, so it's in RPMs. It's got a 0 offset. Okay, and we're working on this one signal. Our Kvasir Database Editor 3, another free download from our website. Quick example here. I've loaded an example J1939.DBC file in it. I've highlighted the message we're talking about here, which is the EEC1 message. I have highlighted within that message the signal we're talking about, right? The SPN 190, or the engine speed signal. Here are all the signals within that message. When I highlight this message, this pops up on the right, shows me all of the signals within that message for this DBC file. The one we're looking at is in these 2 bytes right here. Okay, so Kvasir Database Editor 3, free download, very useful for understanding, building, editing, modifying DBC files. Here's our entire 8 data bytes again. The DA tells us SPN 190, bytes 4 and 5. The DA tells us that it's in tel format, meaning it's the little byte first. The LSB is first, so the 1.5 is the least significant byte. We write this in hexadecimal format as a 1450, right? Hexadecimal 1450. So we can convert that to decimal. It's a 5200. That's what's being transmitted for engine speed in this message, in this signal. Okay, we can do a calculation based on the resolution that we have from the DBC file, the previous slide, 5200 bits times 0.125 RPMs per bit. The engine was idling at 650 RPMs when I took this data. I was sitting on a truck taking this data, and that's what we were idling at, as set by the ECU. So we now see how to take a signal out of a message and take it apart per the information provided in the DBC file and or the digital annex. Okay, CAN frames transport protocol. One quick mention of transport protocol in classic CAN. If we want to send more than 8 data bytes, a signal that has more than 8 data bytes, in this case it's the vehicle identification number, transport protocol allows us to break it down into 4, in this case 4 different frames of data. It can be many more frames of data if needed. And the VIN used 4. So this is how they're transmitted. I'm not going to go into detail. I don't have time. They're reassembled at the transport protocol of the computer. This representation never goes over the bus. This is the reassembly of the VIN. These are ASCII characters representing the VIN. You can go through that exercise if you like and see exactly how that is done. Transport protocol. Transport protocol in this format is used in J1939 over classic CAN only. In J1939-22 CAN FD, we use something called CAN FD transport, which is a little bit different than this. Transports even bigger bytes of data. The diagnostic message is important to get to. We've got a few minutes left here to talk about the diagnostic message, and I'll go into one last example. Here, diagnostic messages are defined in -73. They can be broadcast, they can be on request messages, as we've seen. Diagnostic messages are defined in -73. Some diagnostic messages are on request, some are broadcast. That's in general true for J1939 messages. Understanding the diagnostic message is very important. And diagnostic trouble codes. A DM1 is a diagnostic message that transmits the diagnostic trouble codes on any given vehicle. I'm going to use that in example 4 so we can understand not only diagnostic messages, have an example of a diagnostic message, DM1, a very common one. We'll also understand the diagnostic trouble code here. So a little bit about diagnostic messages in general. They're typically used to report the history and the current state of a vehicle or an engine. It's a legislated format in the US by CARB, in the EU by Euro 6 or 7 standards. Primarily used for emissions-related fault detection and reporting. Standardized across the manufacturers. Scan tools read these codes. And again, they're all defined in -73. That's where you learn about the diagnostic messages. There are 59 of them now. We're defining number 60 right now at the committee level. So the background of diagnostic messages. A diagnostic is a piece of code that performs a test under certain conditions and will set clear or a flag that indicates there may be a problem or a question on this engine or a code. This is a diagnostic. The diagnostic is represented with a diagnostic trouble code, and there are 4 things it breaks down into. The suspect parameter number, we know a little bit about those. That's the biggest part of a diagnostic trouble code. There's a failure mode indicator we'll give you an example of, a conversion method, and an occurrence count in that DTC or diagnostic trouble code. So let's look at DM1 to further understand diagnostic messages and diagnostic trouble codes. So we know the SPN. We've looked at the SPN, an identifying number associated with a parameter or signal. Everything in J1939 has an SPN to identify it numerically. That's important. The examples of the failure mode indicator I mentioned, here's FMI1. If FMI equals 1, data is valid but below normal operating range and the most severe level. If you're in FMI2, your data is erratic, intermittent, or incorrect. Okay, there's 31 FMIs that indicate different things. I'm not going to run through all of them. Conversion method is pretty much refers to an old method of understanding the DTC. It's 1 bit. Occurrence count is how many times this failure mode has happened on this SPN. How many times has this failure mode occurred within this SPN since it's last been cleared? And there's a few bits that are explained there. We're going to kind of blow right through this one because this just shows, in my example 4, my DM1, this just shows what we already know. This shows the identifier phase and how it breaks down into the PGN, which identifies DM1. the source address, that kind of thing. Source address in this case is the engine ECU 00. We're going to look at the data. Let's look at the data here. Okay, so we're actually going to skip the first 2 bytes of the data. I have underlined the 8 bytes of the data. We're going to look at these 4 bytes first, which represent a diagnostic trouble code. Diagnostic trouble code, we know, breaks down into 4 things. The SPN, we're going to look at bit level again, because it breaks down on the bit level, not just the byte level. Okay, the SPN is, in this case, this example, is hexadecimal 66, which equals decimal 102. Okay, and then there's the failure mode indicator. The failure mode indicator here is a 2. We know a failure mode indicator of 2 we saw as an example is data erratic, intermittent, or incorrect. SPN 102 is the engine intake manifold number 1 pressure. So what is this diagnostic trouble code telling us? It's telling us the engine intake manifold number 1 pressure has data erratic, intermittent, or incorrect, and this has occurred 1 time. Okay, that's all outlined here in -73, a couple of cuts out of 73 that show what this is. That's a diagnostic trouble code. One example of a diagnostic trouble code within a DM1. Okay, let's go back and figure out what these first 2 bytes were. So this little cut out of -73 shows a DM1 and what the format of a DM1 is. So we've got A, B, C, and D identified. A is lamp status. That's the first 2 bytes, in this case 43FF. That shows you what lamps are on, off, blinking, clear, whatever, according to this little data down here. Okay, and shows you what the lamp status is. That's these first 2 bytes. We know the next 4 bytes, that's diagnostic trouble code. That's a code, 1 code set on this vehicle. If there were more codes to report in this DM1, how would we do that? Well, we would repeat another diagnostic trouble code out here following this one. Right now we only have 1 code. We have a total of 6 bytes out of the 8. So we just put filler and FFFF in the last 2 bytes. If we had 2 codes on this vehicle, you don't repeat A, you don't repeat the lamp status. It's given 1 time. You repeat, as shown down here, BCD, BCD, and BCD. You repeat those once every time for every code you have set on this vehicle, or every DTC. So if we had 2, our data would go to needing 10 bytes. We can no longer fit that in one classic CAN frame. We have to go to transport protocol. Okay, if we have 2 or more codes set, the DM1 will use transport protocol to communicate its data. Transport protocol as I've defined in a previous slide. All right, I know that's a mouthful. I know that's a lot. There's a lot more to it. J1939 takes years and years to really get a full understanding of. Hopefully I've given you some basics and some ways to jump in and learn this stuff through examples. I like teaching through examples. Okay, some conclusions. Own the standards, buy the standards, fully research the subjects you want to work on through the standards, and really try to understand them. I try to understand from the bit level on up to the application. I know some new engineers do it the other way around. I'm an old timer. That's how I've done it. Right? Be able to follow a signal back to the data link layer. You don't really have to follow it down to the bits in the physical layer. Physical layer is a physical layer. If it's doing its job, you're good. But be able to go back to the data link layer. Identify those bytes, those hex codes, those 1s and 0s. See how that comes. Confirm what the tool tells you at least a few times. Sometimes tools make a mistake. If you don't understand something, be able to trace it all the way back and figure it out from the data link layer. Okay, own the J1939 digital annex. Turn the filters on, know how to use that spreadsheet, and know how to use the filters to look at the data within that spreadsheet and find what you need to know. There's a lot in there. It's great information. It's a really neat, well thought out protocol. Been working with it a long time. I really hope that many of you who don't know it well will get a jump start from this presentation and learn it. We're going to move on to the next presenter here and hopefully give you some good information about the software stack, how to make things easier for you by using some additional software from our partner company related to J1939. Okay. Where to get more? SAE.org for the standards, emotas for protocol stack, emotas or Kavasa for some training. Check out those places. I am done. Right at my time limit here. I thank you for your attention.
Hello, my name is Torsten Gedenk, and today I'd like to present you something about our J1939 stacks and tools. At the beginning, I will say something about the company emotas, because we might be not that well known like Quasar. Then I'd like to say something about J1939 protocol stacks, and the main part of my presentation will be how the J1939 protocol stack and device designer can help you with the development of J1939 devices. And finally, I will show you our tools to interpret and to transmit J1939 messages. We at emotas are a CAN software solution provider. That means that we are specialized in CAN, and we provide various CAN software solutions for different CAN or CAN FD based protocols, such as CANopen, CANopen FD, J1939 of course, and also other protocols like ISO-DP or UDS. It means we offer stacks, bootloader to update the firmware, tools to design devices with these protocols, and we also offer services like training or consulting around all of these protocols. Well, today the topic is J1939, and these are the tasks of a J1939 protocol stack in my point of view. Well, one could argue if CAN reception and transmission is part of the stack, well, it is needed in all cases, but if you, for example, use the stack on a Windows PC using a Quasar interface, of course the CAN interface and the CAN lib would handle CAN reception and transmission. But if you use the stack on a microcontroller, at least we provide all the source code which is necessary to handle CAN reception and transmission. Well, if you look at the J1939 services, of course, any J1939 stack shall support address claiming and commanded address handling. And of course, it shall support reception and transmission of simple 8-byte BGNs, but also all transport protocols like broadcast announcement messages and CMDT. And of course, the stack shall assist you in splitting the PGNs into multiple SPNs, and by applying the scaling and offset values to the raw signal, so that the application gets the real values. Additionally, if you want to support J1939 on CAN FD, such a protocol stack should support the multi-parameter groups and optionally maybe diagnostic messages or J1939 safety messages. Before I show you the J1939 stack in detail, I like to show you a bigger picture of our stacks and tools. Here in the middle is or shall be a J1939 application, and it consists of some user code. For example, if you develop your own device, maybe a temperature sensor, you will need some source code to measure the temperature. But if this temperature sensor shall communicate using J1939, you will need a J1939 stack as well. And along with our J1939 stack, there is a tool called J1939 Device Designer. And in this tool, you specify which PGNs and SPNs you want to send, and you configure the stack. And this tool generates some source code files, and all these have to be compiled and linked together to build your application. If you want to update your application via J1939 in a J1939 network, you will need a J1939 bootloader and some tool which is able to handle the firmware update of your devices via J1939. I don't want to go into the details of this now, but I just like to mention that we also offer tools for this and J1939 bootloaders as well. Well, once you have your application ready, you might want to monitor the CAN messages, and well, looking at the raw CAN data is the first step, but it's always easier if you have tools which are able to interpret the CAN messages according to J1939. And both our CAN interpreter and our Device Explorer are able to interpret J1939 messages with a so-called J1939 extension. And both of these tools use a quasar CAN interfaces, so you can use your quasar CAN interfaces for them. Also, you could use our J1939 stack on a Windows PC with the quasar CANlib and CAN interfaces. Most of our customers use the J1939 stack on microcontrollers, and well, we support different families of microcontrollers, like for example STM32, Infineon XMC, or many more. And well, and even if you don't support the microcontroller you want to use, you can use our J1939 stack anyway, but you have to provide by yourselves functions to send and to receive CAN messages. Well, as mentioned on the previous slides, the J1939 device designer is the tool which we use to define which PGNs this device shall send or receive. For example, here one can define individual PGNs, or you can import them from DBC files or from other sources. In this example, it's the engine temperature 1 here, and it's defined to be sent every second, and the stack just sends them. For each SPN, we have a variable assigned, and the application just has to fill the variable, and then the stack takes care about the transmission of this PGN. It happens in the same way if you want to receive PGNs. For example, here we have a 16-byte PGN, so the stack will just use a transport protocol to receive it, and once the reception is complete, it will write the values into this variable, notify the application about it, and the application can use the values from these variables. But some customers don't like global variables, and we also have a solution for that. In that case, the stack itself will handle the memory for these SPNs, and there are API functions to read or write these values. Additionally, besides defining the signals, the device designer is used to configure the stack a bit, so you define which services are supported if you want to use SPAM, CMDT, and other services. And you can specify which or if diagnostic messages shall be supported and which shall be supported. And based on that, this device designer generates some .c and .h files, and they have to be compiled and linked together with the stack, and then you can build your application. On this slide, I have summarized some of the API functions of the stack. The basic idea is that one can register callback functions which are called at specific events, and then the callback function, for example, informs the application that a PGN had been received. Additionally, there are SPN access functions to put or get the value of different SPNs, for example, if you don't like to use variables for them, and we have specific functions for each data type. And we also offer specific functions for diagnostic messages. This example here shows the functions for diagnostic messages 1, but we offer specific functions for each diagnostic message. And there are also functions, for example, to convert the raw CAN values to the displayed values and vice versa, and we provide these so-called slot functions for all slot conversions. And additionally, there are functions to send PGNs asynchronously. So if you don't want to send it cyclically, you can just call a function and the stack will send the PGN, and it doesn't matter which transport protocol it needs to use. It finds it out by themselves and just transmits the PGNs. And we also have functions to request PGNs. After you have finished your J1939 device development, you may want to look at the CAN bus to see the CAN messages. Well, you could look at the raw CAN IDs or data, but it's better to use a tool which is able to interpret the CAN messages according to J1939. And both our CAN interpreter and our device explorer provide a J1939 interpretation. Here you can see, for example, that it was an address claiming a message like this, or here we have the engine temperature messages with the values of the PGNs and SPNs. And if you don't want to have this view, you can look at the so-called object view, and then in that case you can select, for example, a specific PGN, and you can see the changing SPN values here. And well, also for this PGN. And if you want to see the changing values in a chart, you can assign them to a plot, and then the data will be received and plotted. Our data plotter here can show a subs or any selected SPNs with their values, and you can see the values changing here, and you can afterwards also export the logged values in a CSV file and process them afterwards. Very often, if you want to develop a J1939 device, it is useful to transmit J1939 messages, and our J1939 transmitter can do that. Can, for example, specify any PGN or the PGNs in your project and send them with specific values. And it doesn't matter if the PGN is longer than 8 bytes or shorter. Can just specify the values here, and then it will send this PGN accordingly. And this PGN transmitter also supports address claiming, some but not all diagnostic messages, and CAM11 and CAM21. So it supports a lot of different J1939 messages. Well, that's my last slide today, and I hope I could present you some useful information about our products. If you have additional questions, please ask me afterwards or contact me by email or phone if you're interested in our products. And I also would like to highlight that there will be a J1939 remote training hosted by us November the 18th. We'll start at 10 a.m. until 4 p.m. Central European time. And in this remote training, we will explain the details of the J1939 protocol. If you're interested in it, and if you need more information, please visit this website. And again, I'd like to thank you for paying attention, and bye-bye.